Good day. Welcome back to the lectures in statics of rigid bodies. So, the previous lecture was about the introduction of the subject and the Newtonian mechanics. Now, to fully start with the course or the statics of rigid bodies, it is vital for us to first be knowledgeable in vectors. So vectors can be used in analyzing bodies in 2 dimensions and in 3 dimensions. So to know more about vectors, I have included this in the course outline or in the course of statics of rigid bodies. So this will help us in easily analyzing 3D structures, but vectors are not commonly used in two-dimensional analysis. However, it is more popular when it comes to 3D. So to start with analyzing vectors, in this lecture, you may need to have a pencil, a ruler, protractor, calculator, millimeter paper, graphing paper is also okay for optimal understanding. Now let's define first scalar and vector. Vector and scalar is quite different quantities. Scalar quantities only consist of magnitude, whereas vector has magnitude and direction. So for example, the real numbers shown here as a scalar quantity, and also temperature, time, speed, those are scalar quantities, but the vector quantities are force. So when we say force, you have to say the direction of the force. So if it is applied to the right, upward, downward. Also velocity is a vector quantity, which means that the direction of your velocity should be specified and also your acceleration. So again, the difference of scalar is that scalar has no direction. So if you're trying to explain or you analyze temperature, definitely it has no direction. Whereas if you're analyzing the velocity of a certain object, its direction must be defined. Okay? Scalars are written as italicized English or Greek letters. In this lecture, we are using italicized letter for scalar quantities, and we will use bold letters for representing vectors. So if you want to get the magnitude of a vector, we can use the absolute value sign, or we can simply rewrite the vector in bold letter in italicized form to have its scalar equivalent. Okay. So this one, this vector has a magnitude that is A, or written in italicized form, and it is scalar because the magnitude is scalar. Any vector A can be represented geometrically as directed line segment or an arrow, as shown in this figure. So you can define a vector with its magnitude. So when we say magnitude alone, it is written in italicized form, and its direction. So this one is already in vector form. However, you can still write the vector A here in bold face letter, still with an angle theta. So there's two way of representing a vector here. Positive angles are measured counterclockwise to the positive axis, and vice versa, negative angles are measured clockwise from the positive axis. Now let's define two vectors A and B. They're said to be equal if their magnitudes are the same. So if the magnitude of A, the A here is in boldface, the magnitude of A is here, A in italicized form, and the magnitude of B is here. If they are equal, then they could probably, vectors A and B could probably be equal, but they have to satisfy the second one, which says here they should have the same direction. So if two vectors can satisfy the first and second condition, then A and B are equal. The multiplication of a scalar m to a vector A, written as MA or as AM, is defined as follows. So if m is positive, MA is the vector of magnitude MA that has the same direction as A. So recall that m is simply a magnitude. Then if it is positive, this would not really affect the direction of A, because the sign of A would remain positive, because any number you multiply with a positive integer or a positive value would have the same sign after it is multiplied. However, if you try to multiply a magnitude m that is negative to a vector A, then the sign of A would be the opposite of the sign of MA would be the opposite of vector A, because if you multiply a number to a negative value, you would have its opposite sign. So MA is the vector of magnitude MA that is oppositely directed to A. So again, if M is a scalar quantity multiplied to A, which is a vector quantity, the magnitude would be MA and would still have the same direction as A. But if M is negative, the magnitude would still be MA, however, it would be opposite to the original direction of vector A. Now, if M is 0, this would be a null or zero vector, because if you multiply 0 to a vector, it would have a zero value. Now let's define the unit vector. The unit vector is a dimensionless vector with magnitude 1. Therefore, if lambda represents a unit vector which has a magnitude equal to 1, then it has the same direction as A. We can write now that the magnitude of A is A, and the unit vector is the one or the vector that gives direction to the scalar A. Then this is the unit vector. Okay, so we can break down this vector into two components, where A is solely the magnitude and the unit vector gives the direction to the vector A. Okay, this representation of a vector is often useful because it separates the magnitude and the direction. So again, we can rewrite this vector A into two, where we can easily see the magnitude and the direction. So that's the purpose of unit vector, to give direction or to analyze the direction of the vector. So for the graphical method for adding vectors, we have different methods. The first one is parallelogram law for addition. So addition of two vectors, A and B, is defined to be vector C, as shown. So let's see. So we have vector A and vector B. So this one way of writing vectors, you have here the arrow and the name of the vector in boldface, likewise here. So these two vectors are plotted, so they are arbitrarily plotted, and to get the sum of the two vectors C, represented by C, this will be the diagonal of the parallelogram formed by vectors A and B. So therefore, if vector C is the sum of A and B, we have here A plus B equals C. And the way they determine the value of C is by parallelogram law for addition. So if C is the sum of vectors A and B, we call B and A as component of C. Likewise, or on the other hand, we call C as the resultant of A and B. So this is the parallelogram law, wherein you create a parallelogram out of the two vectors, then diagonal would be the sum of that two vectors. Now, there's also another way for having the sum of two vectors, and that is the triangle law for addition. So here, we draw the two vectors from tail to tip. So if we want to add the vectors, let's start with the first vector A. We draw its tail to its tip, and now we want to add B to A. We will write B to the tip of A, and then let's proceed to the tip of B. Now, to get the sum of the two vectors, we simply connect the tail of A to the tip of B, where C is the vector that completes the triangle drawn from the tail of A to the tip of B. Now, the result is identical if the tail of A is placed to the tip of B. So, if you try to draw the B vector first, then connect the A vector, the value of C will still be the same. So the properties for adding vector, we have the commutative, wherein E plus F is equals to F plus E, which I have said that if you whichever vector you try to add first will yield to the same resultant. And associative, which means if we have E plus F plus G and you add first FG before adding to E, then you will have the same value if you add E and F first before adding G. So that's addition of vector. So for the polygon rule, it is applicable for adding two or more vectors. So we have E, F, and G here. So we can start by adding first the two vectors EF to form a separate vector EF. Then this vector EF could be added to vector G to form the vector EFG. So that is the property here. So if we want to get the value of H, that is equals to E plus F plus G, or E plus F plus G, or you may use E plus F plus G, whichever will yield to the same answer, H. Now for the subtraction of two vectors written as A minus B is defined here. So if you have two vectors, A and B, so if you subtract the value of B to A, so the value of B, if it is negative, it will be directed to its opposite side. So the value of B would be here, and the value of A still remains because this is positive, and this is from the original value of B, which is positive, would be negative, and applying the parallelogram law, A minus B would be in this direction. But if it is A plus B would be in this direction. So trigonometric methods for adding vectors. So we can use the law of sines from the trigonometry, wherein A over sine alpha equals to B over sine beta equals to C over sine lambda. And also, for the law of cosine, we have here. So to fully appreciate the topic, let's have a sample problem. There's two vectors with magnitudes. A is equals to 60 meter and B is 100 meter. Our objective is to determine the resultant of the two vectors A and B. So the first thing we do is to draw the tail and tip of vector A. So start with drawing vector A from tail to tip, and then connect vector B from the tip of vector A. Now, we will draw the resultant, which is the sum of vector A and B, and we can use trigonometry to analyze the magnitude or the length of vector R and the direction of vector R. Now let me just move the drawing here. Just move the drawing here. And to get the magnitude of R, we want to use the cosine law, since A and B are given and the angle in between A and B is also given, or the angle opposite to R is given, then we can solve for R by substituting the values. We have the equation r squared equals 60 squared plus 100 squared minus 2 times 60 times 100 times cosine 140. So this is 1, and the values substituted here, and this one. So pressing that your calculator yields to the answer of R, which is equal to 151 meters. And that is the magnitude of R. We only have the magnitude. We're still looking for the direction in order to define vector R. So to get the direction of vector R, we can still use the cosine law, but sine law is okay, but I will discuss why I prefer cosine. So in this case, we are looking for this angle alpha. So if we get this angle alpha, we can determine its angle measured from the positive axis. Now using cosine law, we have the value of R, the value of A, and the angle opposite to B, which is alpha. So substituting the values, we have 100 squared equals 151 squared plus 60 squared minus 2 times 151 times 60 cosine alpha. And solving for the angle, we have 25.2 degrees. Now, to make it standard, let us measure the direction of vector R to the positive x-axis. Now we have theta. Theta is here. Now we can say that the direction of vector R is 55.2 degrees measured from the positive axis with a magnitude of 151 meters. So we have now the magnitude 151 and the direction 55.2 degrees from the positive axis, and that is your resultant vector from components vector A and vector B. So this is why I use cosine law more than sine law for triangles dealing with interior angles, because as we all know, interior angles for a triangle varies from is greater than 0 degree but is less than 180 degree. So let's try to recall your unit vector. So remember that from a unit circle, the y component of a segment that is equal to 1 is the value of sine. So in here, sine 30 is equal to 0.5. And also, sine 150 is also 0.50. Now, if you have a value of 0.50, you could probably have two values of sine or two values of angle, which are 30 and 150, and are both qualified for being an interior angle of a triangle, which is, if you're analyzing cosine for an angle of in between 0 and 180, there would be no repeating value of angle. Okay, let's try another problem. So the vertical force P of magnitude 100 kN is applied to the frame shown in figure. You will resolve P into components that are parallel to the members AB and AC of the truss. So recalling the triangle law, P is the sum of PAB and PAC. Now, this would be the drawing, but let's try to analyze how we get this triangle. So first, you can see this is AB. That's also equal to this one. Okay, that's AB. And this is your P, and this is your AC. So again, we have AB, AC, and P. And if this is 70, so this one is 70 minus 35, you get this 35-degree angle. And if this is 35, this is 35, this is 70, and this is 70. So by alternate interior angles, this would be 70. And with that, we can say that this is a supplement of 70 and this is 110. So to complete the interior angles, this one would be 35. Okay? And that would yield to this diagram here, wherein the resultant P is connected from adding vectors PAC and PAB. So if we add PAC and PAB, we start drawing PAC, then connecting PAB, then to get the resultant, you start by drawing it from the tail of PAC to the tip of PAB. That's how you add. So again, PAC plus PAB, then their answer is drawn from the tip to the tail. So we have the diagram here. So make sure that all the interior angles are properly labeled for the ease of analyzing the problem. So PAC and PAB have the same inclination as member AC and AB respectively. And we can have the value of PAC using sine law. And why I am now using sine law, because the angles are already given, so we don't have problem with sine law. We can solve for PAC now using sine law, wherein that is PAC over sine 110 equals to 100 over sine 35. So sine law is simply the numerator is the magnitude and the denominator is the sine of the opposite angle. So that is PAC over sine 110. And if you want to have here this one, because if you use this side, you would definitely have two unknowns. So let's use this one. 100 over the opposite is 1/3. So now we get the value of PAC, that is 163.83. And also we can get PAB using sine law, that is PAB over the opposite angle, and still using the same value here, 100 over sine 35. Then we can say that the value of PAB is 100 kilonewton. Now for the direction, you can measure it using geometry from the positive x-axis. So another problem, the total aerodynamic force acting on the airplane has a magnitude of 6 to 50 Newton. To solve this force into vertical and horizontal components called the lift and the drag, respectively. So the force vector F is the total aerodynamic force. It has a magnitude of 6 to 50. So this aerodynamic force causes the airplane to maintain its altitude. However, it is not acting perfectly in a vertical direction. It has a certain inclination measured 6 degree from the past from the vertical axis. So it has two components. So this F equal to 6 to 50 has two components, namely Fx and Fy. So the F is the resultant force. We are looking for the components Fx, which is the drag, and Fy, which is the lift. So this vertical force, that's why it's called the lift, because it is directed upward. And that's why this is called the drag, because it is dragging the airplane against its direction of flight. Okay. So as you can see, 6 degrees is here. So I just exaggerated the drawing for ease of analysis, but 6 degrees is very minimal, is a very acute angle. So we can determine now fx and fy by trigonometry. So using sine function, if we have the value of f is equal to 6 to 50, then assign, 6 degree here. So we can compute for fx using sine function and this equation. And substituting the values of f in the equation, we have now the value of fx equal to 653.30 kilonewton. Now that is the drag force. As you can see, it's small compared to the magnitude of F. So most of the force goes to the y component or the lift force. So to get the Fy or the lift force, we use the cosine function, and that is cosine 6 degree equal to Fy over F. So substituting the value of F, we have now the value of Fy equal to 6,215.76 kilonewton, and that is the lift force. So another problem, there's two tugboats applying forces P and Q to the barge, where P is 76 kilonewton and Q is 52 kilonewton. So we want to determine the resultant force of the two tugboats. Say this boat is being pulled by two tugboats, so we want to know the direction of this barge due to the force exerted by two tugboats. So it is ideal for us to draw the two vectors. So let's start by drawing vector Q and then drawing vector P. So that is from end to tip, no? So from tail to tip of Q, then P is connected to the tip of Q. So the resultant force of the two tugboat represented by R is drawn from the tail of Q to the tip of P. Now, our next problem is the geometry of this diagram. So to get that, let's first have the magnitude. The value of Q is 52 and the value of P is 76. Let's try to have the angle. So by using tangent, we could determine this angle equal to 26.56, and that's simply tangent theta equals to 12 over 24. That yields to 26.56. So we try to plot that here. That is 26.56. Just this resultant is not really acting on the vertical axis. It's just so happen that's a very minimal angle from the vertical axis. So 26.56 is here. And using alternate interior angles, the property of alternate interior angles are congruent. Therefore, this side is 26.56. Now, using another tangent function, this angle is 26.56, and that is here, measured not from the resultant but from this axis. So that is 26.56. Therefore, this angle is also 26.56. Now, to have a right angle here, since this y-axis and x-axis is orthogonal, therefore, the angle in between P and Q is 36.87. Now, let me just move this drawing here. Just move this drawing here. So the drawing is already here. So we can get the value of the resultant using cosine law. Since we have the magnitude of Q, the magnitude of P, and the angle opposite to R, we can solve the value of R. So that is R squared equals Q squared plus P squared minus 2QP cosine 36.87 degrees. Now substituting the values of the values of Q, we have 52, the value of P 76, and directly substituting this one, we get the value of R equal to 46.44. Now we have the magnitude. The next thing we do is to get the direction of the resultant, and that is the angle beta. Now, if we know that this is 26.56, this is 36.87, we can still use the cosine law for this one, since we know the values of R and Q and the P. Now, the angle beta is measured from this one. Remember that we cannot directly get that the sum of interior angles for a triangle is 180 because this one is not measured from P to R. This is measured from P to the vertical axis. So getting the value of beta could be possible by using the cosine law. Since P, R, Q is here, these two are given, R and Q, and cosine beta is unknown. So we can simply just substitute. P is 76, R is 46.44, Q is 52, and the rest here. So we have the value of beta equal to 100.92 degrees. Now, to measure the direction of the resultant R from the positive horizontal axis, we would just simply subtract 26.56. Since this beta we determined from the cosine law is the angle between vector R and vector Q. What we want to have is the angle between vector R and the positive x-axis. That's why we subtract beta with 26.56 degrees. Now we have the angle theta, 74.36 degrees, and that is the angle of the resultant. So now we represent the vector here, that is 46.44 kilonewton, having a 74.36 degrees from the positive x-axis. Okay, so to fully master this topic, I encourage you to answer this practice problem. You may want to pause the video to copy this one and answer this application problems with the figures shown here. So thank you for watching the video. I hope I have imparted you some lectures, and again, thank you very much.